So, welcome everyone. I am Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach Specialist for the University of Hawaii Institute for Astronomy. We really wanted to take a moment to say thank you to UH Maui College for hosting these talks, and let's give Dr. Larry Harrison a round of applause. Larry is the astronomy instructor here. So Larry's the astronomy instructor here. So if you want a great class in astronomy, now you know where to go. Thanks to the rest of UH Maui College for supporting us. For those who have been following these public talks, and I said this exact same thing last time, for those of you who have been following these talks, our speaker needs no introduction. Guy Jetty this is his 10th talk. So he's given more talks than anyone else. He spent, yes, and they're all very, I think you'll all agree, those of you who know will agree, they're very beautiful talks. They're really wonderful. So Guy spent 37 years with the Air Force. The last 15 of those years was with the Air Force Research Labs, and in particular the Space Vehicles Directorate. So as I like to say, this is a rocket scientist. He's now affiliated with the University of Arizona, where he teaches some astronomy classes. And so we'll turn the time over to Guy, and let's give him a warm Maui welcome.
Cosmic rays, extragalactic visitors from beyond. And this chart doesn't have any significance, especially with the mailbox, but I just think it was kind of cute. So I put that chart up there, especially since some of you came just for the charts, right? So I don't want to disappoint you. So cosmic rays are fascinating. As you'll see, there's a lot to them we'll talk about in the next hour, hour and a half. This is a balloon that went up in the air, was launched in 1912, and this individual, Victor Hess, he was a physicist that worked for the University of Vienna. And at the time, scientists didn't know whether cosmic rays came from the ground, the Earth, uranium, radon, things like that, whether they came from the atmosphere, from space. So he took a balloon up to 16,000 feet, and he had some instrumentation, and he measured the ionization. The ionization as he went up from ground level to 16,000 feet increased. What that ionization means is there was radiation coming from above, and that radiation was hitting molecules in the atmosphere, and those molecules were losing electrons, and they were becoming ions being positive charged protons rather than being regular molecules. So he is credited with discovering cosmic rays in 1912. He did get a Nobel Prize. He lived a nice long life to 1964. He received a Nobel Prize for his discovery in 1936, because sometimes it takes a few decades to get recognized a Nobel Prize. And as you may know, if you pass away, you cannot get a Nobel Prize after you've passed away. So he fortunately lived long enough, he received his Nobel Prize. So we'll get rid of that balloon. Up and away, and yes, question?
You said he went looking for where they came from. How did he know there was even a thing called cosmic rays?
Oh, well, he didn't know he knew there was radiation which could be measured on the ground. We could measure radiation. We couldn't tell whether it was coming from the ground or from the sky. So that's why it took a while. It took a situation in 1912 going up about 3 miles, 16,000 feet, and he had enough instrumentation, sophisticated enough to see that the rays were increasing by virtue of the increased ionization, and they were coming from space. So that's what happened. Now, what is interesting, this individual, Robert Millikan, he actually was the one that came up with the term cosmic rays, because Hess didn't call them cosmic rays. But Robert Millikan, who was quite instrumental for a number of years at Caltech in Southern California, he is the one that put the nomenclature cosmic rays in about 1925. What's interesting, Millikan thought that they were radiation rays, electromagnetic waves, okay? Whereas Hess thought that they were particles. And there was a scientist, Compton, at the time, who basically proved that these cosmic rays were not rays, because rays usually go with the terminology electromagnetic radiation. So Compton proved that they were in fact particles, but they never changed the name to cosmic particles. Although cosmic rays has more of a cool name, I think, cosmic rays versus cosmic particles. But Millikan was pretty well known too. He came up with this new nomenclature in 1925, and he received the Nobel Prize himself in 1922 or 23 for working on the photoelectric effect. So that's the background in terms of cosmic rays. Now, here's a nice schematic. You have cosmic rays continuously coming into the Earth, and what's happening, they, for the most part, don't make it all the way to the ground. They hit the molecules in the upper atmosphere, and as shown here, they hit these other molecules, and they create secondary particles, many secondary particles. So they will hit molecules, and you see here, they will just, in some cases, thousands of particles. One particle, well, it's kind of it's basically a billiard game or whatever. You have a cosmic ray hitting a particle, that breaks up, it hits other particles, and it just continues to hit particles, and you have all these secondary particles, which many of which reach the Earth. And we'll talk about that in a minute or so. And here's an example, a little bit of a schematic. Here they come, they hit the upper atmosphere, and they hit other particles that are created, all types of particles, and we'll see what those are in a second, which make it to the surface of the Earth. So, what are these cosmic rays composed of? Well, for the most part, 89% are hydrogen nuclei, protons, if you will. So that's most of them, 89%. They think about 10, 11%. I always like the exactness of these numbers. Yeah, sometimes I think the number the precision doesn't match the accuracy. But helium nuclei, about 10%, and then electrons, neutrinos, and metals, the other 1%. But the 11% would be in addition to the 89% that's hydrogen nuclei or protons. Metals, by the way, from an astronomer's perspective, if you're not hydrogen or helium, you're a metal. So you only have two elements that are considered to be non-metals, hydrogen and helium. Everything else, starting with lithium, which is number 3 in the periodic chart, beryllium, boron, everything all the way up to uranium are considered metals by astronomers. This chart, it shows the distribution of the first 40 elements, by atomic number, the first 40 elements. And what's this telling us, which is very interesting, the solar system abundances, you can see hydrogen and helium, very high. Now, realize this is a logarithmic scale. For example, there is 10 times more hydrogen than there is helium in the solar system, okay? And in the universe in general. So that 10 times is belied by the distance. You have to realize you're 10 to the 4th, 10 to the 2nd. So each of these are 10 times the previous. So you have this low number of atomic number 3, 4, and 5. This low number here is lithium, and then that's beryllium and boron, which are a lot less than the abundance of these elements in cosmic rays. The blue line shows the cosmic ray abundances of these elements. So it's just fascinating that cosmic rays have a much higher abundance of these 3 elements, lithium, boron, and beryllium, than it's in the solar system. The other thing is of interest, this gap right here, there's 5 elements that also show more abundance in cosmic rays than the frequency within the solar system, and those are scandium, titanium, there is vanadium, there is manganese. So there's 4 elements that also have higher abundance in cosmic rays, which leads you to believe, well, they're not in the solar system, so these must be coming from somewhere outside of the solar system. And this is just another schematic showing that same information. And again, repeating the percentage that's considered hydrogen nuclei, helium, and others. So the galactic cosmic rays, they're coming down. This is a nice little cartoon. They're hitting atmospheric atoms, and they're breaking out into different components. The next one really shows what these are. So you have a cosmic ray, a primary cosmic ray coming in. It hits an atom, and there's lots of atoms. There's nitrogen, most of the atmosphere, about 80%, and only about 19% is oxygen. The rest is various elements. So it hits an atom, could be oxygen, but mostly it's going to be nitrogen. And then that breaks out into secondary particles. And I think about 50 initial secondary particles are produced after the first collision. So these are pions. Okay, pions are subatomic particles that are created when the cosmic ray, most likely a proton, hits an atom, most likely a nitrogen atom. So you have pions, and then the pions have very short life. They quickly disintegrate, and the pion without a charge right here, that actually expels, if you will, gamma rays. So the gamma rays are being created by these pions, and eventually the gamma rays break down into electrons, the E's, okay? Pions also create a large number of muons, M-U-O-N-S, muons. And these muons are created by most of the pions. The pions have a very short life, it's almost instantaneous, and the muons are responsible for a lot of the particles, the secondary particles, and for that matter, they're probably tertiary third particles or even fourth level particles that hit the surface of the Earth. And you have neutrinos. The V with a sub-muon are neutrinos. You have a lot of particles. Now, this is a standard model of subatomic physics, and you can see most recently they added the Higgs boson. What's of interest is the electron and the muon. They're both negative charges, but you'll notice on the weight, if you look at this weight here, you don't need to worry about the MeV, but the 0.5, and this is 105, the muon is over 200 times heavier than electron. Electron's not that heavy, but the fact these muons are 200, I think it's 207 times as heavy as an electron. One of the reasons why they are quite powerful. Once they hit the Earth, they can go down like 10 meters, 30, 40 feet in the ground. They can go through buildings. Right now, as I talk, every second, a muon is going through my hand. And if we'd have a little pad, probably in the last, I've been here, 10 minutes, we've probably had hundreds, if not maybe 1,000 muons go through my hand. Now, if you have an area on the ground that's 1 meter square, in 1 minute, 10,000 muons will hit that square. And most of those will go underground. Let's talk about cosmogenic nucleosynthesis. Okay, this is a periodic chart. Most of us are familiar with this chart. What's interesting, I love this chart because current understanding of how these elements were created. Well, we've known for a long time that hydrogen and helium created in the Big Bang some 13.7 billion years ago. And they think maybe some lithium was also created in the Big Bang. However, they have discovered recently, I think it's only in the last 40 years or so, they've discovered that the lithium and beryllium and boron, those three elements after, atomic number 3, 4, and 5, these three elements, for the most part, were created by cosmic rays. And that's called cosmogenic nucleosynthesis, okay? The cosmic rays, even when they're going through space, they're hitting molecules, and they are creating lithium, beryllium, and boron. And then once they get even into the atmosphere, they create these elements on Earth and also in the solar system. They're also thinking now that there's others of these articles, there are isotopes being created by cosmic rays. One of them was aluminum. They think aluminum is one of these that's being created by cosmic rays through this cool terminology. It began the test, cosmogenic nucleosynthesis. And not only aluminum, but iodine, chlorine, and neon. They believe that some of those elements were created by cosmic rays. And the terminology they use also is cosmic ray spallation. Spallation is the actual creation. That's the process that's used. And once they are created by nuclear cosmogenic nucleosynthesis, but it's also cosmic ray spallation. Any questions before I keep going?
If they're made by cosmic rays, why aren't they blue on the chart?
Oh, because the chart. Okay, the question is then, please remind me to repeat the question. If they're made by cosmic rays, why aren't they below on the chart? Because the chart is a couple years old. I mean, the information or the idea that these three elements are created to a large degree by cosmic rays is relatively new. So the chart has not been updated. Just like if you were to redo this now, you'd probably put a little bit of, you would actually make some reference to, well, they do say cosmic rays right here, the blue, but you're saying why aren't the other ones blue? There should be a little bit of blue in chlorine, neon, aluminum, and iodine, to the extent that not everybody necessarily agrees, because some scientists will say, yeah, these likely are created, other scientists say, no, not likely. So you always have this push, back and forth. But you could redo those. The cosmic rays, though, are blue on those three: lithium, beryllium, and boron. Okay, so birthplaces. Where do cosmic rays come from? They still basically don't know, but they have a lot of good ideas. And again, some scientists say, oh yeah, we think it's from here, we think it's from there. But there's several ideas. First of all, someone mentioned the sun. The sun, right over here, does create what we can call cosmic rays. But they're relatively low energy. So some of the cosmic rays that come to the Earth are from the sun, for sure. So they're not the high energy ones, which we'll talk about in a few minutes. Another source that's commonly referred to, supernova. A star basically explodes. I have an example of one coming up, a supernova in 1987 in the southern hemisphere sky. And it was considered to be a type 2 supernova, which means a core collapse. A very large star, the gravity got so much that it collapsed on itself, and that caused a supernova. Scientists think, although I've never seen any positive information, that they have identified cosmic rays specifically from that 1987 supernova that's in the southern hemisphere. And we'll have a little chart on that later on. So that's one pretty likely source. The other sources would be, let's take this one here. This is known as M1, the Crab Nebula. This is famous because in 1054, this star exploded. It was noted by people in China. There are some a petroglyph in Chaco Canyon in northwestern New Mexico. And they think the design in Chaco Canyon is of that supernova that exploded, was seen in 1054. So that's a possible source of cosmic rays. Going on further, let's go to this one right here. This is an active galactic nucleus. If you have a galaxy and it has a supermassive black hole, I mean, our Milky Way galaxy, we have a supermassive black hole of about 10 million solar masses, okay? Which sounds like a lot, 10 million times the mass of the sun. But compared to this one over here, this is the black hole which was imaged by what's called the Event Horizon Telescope, a series of telescopes stretched across the Earth at a number of universities and organizations, and they imaged this black hole. That black hole in the center of M87, which is an elliptical galaxy that is 54 million light years away, this black hole is 6 billion times the mass of the sun. So 6 billion times the mass of the sun versus our massive black hole, our supermassive black hole of only 4 million solar masses. This definitely is a candidate for the creation of cosmic rays. This is another example of an active galactic nucleus, not a black hole like this is, but this is one where you have a lot of infalling matter, and you get so much material going in, you have these jets of very high, rapid, near light velocity streams of material being expelled from this active galactic nucleus of this galaxy. So those are some of the places they think it's from. Now, here's another thing that's really mysterious. There are a number of voids in the universe where there's not many stars. And I've got a couple very powerful cosmic rays coming up, and they have traced them back, and they come from places that don't have anything that looks like it would generate a cosmic ray. So they're really at odds, because they say, we don't see any, we think it's from this void, but we don't see anything in that void which would create it. So that's one of the mysteries of these cosmic rays. Not everybody agrees where they come from, and some people are still at odds. It's not only where they come from, but the power. Some of these super energetic cosmic rays are 10 million times more energetic than we can create in our super colliders, like the one that's in Europe. That super collider creates a lot of very high-speed particles, but it is not even close to the power of a really powerful cosmic ray. So that's the birthplace as we best we understand it, or the possibilities. So continuing, one of the problems in trying to find where these cosmic rays come from is if they're protons, a lot of the biggies are protons, they're charged particles. And as they're being expelled from some location like this, looks like a black hole in a galaxy, millions of light years away, maybe even billions of light years away, because they are positively charged, they go through a lot of magnetic fields. There's a lot of distortion in their path. They can't make a straight shot like this photon pretty much can make a straight shot. And neutrinos make a straight shot. But they cannot, when this cosmic ray is a proton, hits the Earth, and here's the secondary particles, what they try to do is they try to see where the secondary particles are, and they can work backwards to see where it came from. They can't in this case because there's no straight, this situation, they could go right straight back here, but they can't really follow that path back because of the length of time it's taken that cosmic ray to get here and all the electrical magnetic fields it's gone through. Love this chart here. This actually shows the energy level, flux. All flux is a quantity. And what happens is you have a lot of cosmic rays up here that are relatively low energy. We talked about the sun. The cosmic rays up in this realm, we have a lot of them. They have a relatively low energy. And for example, in the 10 to the 9th is a billion. So it's a billion electron volts, and I have a chart defining what an electron volt is. But 10 billion, 11 billion electron volts, they are powerful, but they're not that powerful compared to some that we'll see. And they fall with a lot of them, and they have relatively low power, low energy. What happens is the higher the energy level of cosmic ray, the more rare they are. You're not going to have a lot of high energy cosmic rays. So you get in the realm here, and by the way, frequency is 1 particle per square meter per second. So these are coming out at a pretty high rate, 1 per second, 1 square meter, that's not too bad. You get further down here, and they consider this to be a knee, you get like 1 particle per square meter per year. And these are more powerful. There's fewer of them. They're coming down in number, but they're more powerful. Not a billion, or 10 to the 9, but they're 10 to the 12, which would be a trillion, 10 to the 15, which is, what's after a trillion? Quadrillion? So these are the particles that are higher energy than come from the sun, but most likely these particles are coming from our galaxy through the it could be coming from our supermassive black hole, but there also could be coming from supernova within our galaxy. They could be coming from other objects, other activities within our galaxy. Once you get out in this part of this curve, another angle here, they're very rare, 1 particle per square kilometer per year, and these particles are upwards of 10 to the 18, all the way up almost to 10 to the 21st. That's a 1 followed by 21 zeros. That's a very large number. And these are the ones that they feel are extragalactic. They're from outside our galaxy, from some other galaxy. But there's some confusion because they think they should be relatively close by galaxies because they're so powerful, but yet if they were further away, by the time they got here, they would lose some of that power. So there's kind of a little bit of an intrigue there about how could it be that strong if we can't see where it comes from? And if it comes from something close by, it would make sense it'd be very powerful. Close by being, a galaxy 10 million light years away or 20 million light years away. All very low numbers, right? Close, 10 million light years. So what's a few million light years? Okay, so what is an electron volt? Very simply, it's 1 electron volt is the energy gained by 1 electron when it's accelerated through a potential difference of 1 volt. So apply 1 volt to 1 electron, and that's 1 eV, 1 electron volt. Here is the second most powerful cosmic ray they've ever measured. And it's fascinating because it's hard to pronounce. It's the Amaterasu particle. That is Japanese for, I'll show you in a second. I should have kept that back up there. But this is the Japanese sun goddess. And this was found by a group at the Telescope Array Project in Utah, which is a collaboration among Utah, Japan, and a couple of other countries. And they picked an interesting name to call it the Amaterasu particle. It is 240 electron volts, which is 240 times 10 to the 18. Or if you will, if I had made that chart again, I would move the decimal point over and I'd have 2.4 times 10 to the 20. So 2 and then 20 zeros. Even though an electron volt's not very powerful, you start adding a number like this, it's a billion. 240 billion electron volts. Pretty darn powerful. And this is one where they looked at where it came from. It looks like it came from one of those voids. And there's a lot of voids in the universe. You've seen pictures of galaxies that are formed it's like soap bubbles. Galaxies are formed around the bubbles, and there's lots of voids in between these strings of galaxies. And this one appears to come from one of those voids. Here's an example right here of a void they think it may have come from. So we're right here at the edge, and this void, the Virgo supercluster, that's that Virgo supercluster where that large elliptical galaxy called M87 is 54 million light years away, and it has that supermassive black hole of 6 billion solar masses. So that's right at the edge of this local void, and they think that that particle came from the local void. What's fascinating is that particle never made it down to the surface of the Earth. So they have a detector, and I'll show you some detectors. When those secondary particles are created, the detectors pick them up, and then the scientists have to analyze where those secondary particles, where they were, how powerful they were, and they work backwards to figure out, make a pretty good estimate of how powerful that initial ray was as it entered the atmosphere. Here's the most powerful cosmic ray they've detected. Now, what gets me is, if this is the most powerful one they detected, I'm sure there's a lot more powerful ones they haven't detected, okay? So that's intriguing right there. But this was 320 times 10 to the 18 electron volts, or if you will, 3.2, that's awful precise too, 3.2 times 10 to the 20 electron volts. It was discovered in 1991. The other one was 2000, what was the other one? 2003, let me go back. 2021. But this is fascinating too, because this particle hit 2021, but they didn't identify it to 2023, because it takes a couple of years to go through the data. So in 2023, they said, oops, we found this particle that came into the atmosphere 2 years earlier. And this is important right here, because how much power does this have? It's like taking a brick at your waist level and dropping it, hopefully not on your toe, which leads you to believe, does that mean if you were hit by one of these, you'd feel like it was a brick? Possibly, although fortunately the most powerful ones are so rare that it's likely you won't be hit by one of these things. (1991), that's the most powerful one so far. Now we're going to step back a minute. Here's the Earth. Fortunately, we have this magnetic cushion around us called the magnetosphere, and this helps protect us from some solar radiation, helps us protect us from galactic cosmic rays. However, as we all know, during a solar maximum, which we're kind of still in, we're kind of going off the solar maximum now, but we still get some radiation coming into the polar areas, which give us some pretty nice aurora. I don't know I think some people in Hawaii may have seen the aurora last year. Did you see any of that, Larry, the aurora from Hawaii? I've heard people.
I know in Tennessee, as far south on the mainland of Tennessee.
I think some folks in Tucson saw it, which is 32 degrees, still further north than we are here at about 20. Yeah. But cosmic rays also, we're protected from cosmic rays to some degree with this magnetic field that's around the Earth. Although, I gave a talk this morning to my class, and they're thinking that the magnetic field of the Earth has started to weaken. And they're thinking that what they thought was a solid iron core surrounded by an outer core. They have the inner core is solid, the next core is liquid, and they're now thinking that inner core isn't as solid as they thought, and there's some distortion in that inner core. They don't know what the ramifications are, but it could be going along with some decreasing of the magnetic field. I mean, don't worry about it. It's not going to probably happen in our lifetime, so it's not something to lose sleep over. Okay, so, and who attended the talk last year on aurora? A couple of folks did. So some of these charts, we are now, this was the solar max cycle 24, very powerful storms off the sun, a lot of flares, a lot of sunspots, which generate flares, a lot of coronal mass ejections, because you have the magnetic lines of the sun get twisted and they break and they send out all kinds of material, including these CMEs, these coronal mass ejections. And that was the solar max about April of 24. And then it went down, the low of that solar cycle, it's an 11-year solar cycle, has begun in 2019, solar cycle 25, and now we're in 2025, and I'll show you a chart where we currently are with that cycle. So with that cycle, this is pretty current. This shows, you really can't tell when a solar max happens, when you were at the solar max until it's over. Because you don't know, as these sunspots, and we're measuring sunspots over here, as these sunspots increase, you don't know, they could keep going. You don't really know until it starts to go down. This looks like we've reached the peak of solar max probably late in 2024. It's hard to tell exactly. But this chart is pretty accurate. So we still have a lot of solar activity. I'm getting reports every day on a couple apps that there's still pretty good aurora in the aurora zone, which is over, for example, Alaska. In that aurora zone, they still have some pretty good aurora activity. There's a cycle, 11-year cycle, or if you want to, it's also called a 22-year cycle because it flips polarity. So if you want to go from negative to negative, it's 22 years. If you want to just look at the polarity flipping, it's an 11-year cycle, but it's also called a 22-year cycle. So we've had some pretty powerful cycles here, and they always measured them by the number of sunspots. So, we had upwards of 300 plus sunspots or so, and then the last one, cycle 24, was a real dud. It was like the lowest cycle they'd had in a number of years. And they thought that this was going to be low too. Well, not as bad as last year, but probably not as good as the long-term average over the past maybe number of probably 50 years or so. So the significance of this, and of course they create gorgeous, gorgeous pictures. I brought these pictures just for these ladies that came just for the photographs, right? So enjoy those photographs. Those are beautiful. Okay. Here's the fascinating thing about this. If you plot the solar cycle with the cosmic ray cycle, what happens is, up here is the sunspot cycle. Look at the lows of the sunspots. Every minimum has an increase in cosmic rays. So back here, 1965-ish, low, very little activity on the sun, very few flares, very few coronal mass ejections. You have an increase, significant, probably it could be as much as a 20% increase in the count of cosmic rays. And it happens repeatedly. The low, the minimum, this solar cycle, this looks like 20. You also increase in the cosmic rays, and then it drops down, the cosmic rays, when cycle 21 picks up. Over here, the cycle goes down to sunspots, and the cosmic rays increase. And same way, cycle 22, a lot of sunspots, and you have not a lot fewer, but you have 20% fewer cosmic rays, right up to, as this chart shows, cycle 23, where there was a decrease in the rays. So there's an inverse relationship. This, by the way, was from McMurdo in Antarctica. They have a neutron monitor at the location. So we've had some analysis from spacecraft. Everybody remembers 1977, we launched Voyager 1 and Voyager 2. They went by Saturn, they went by, first Jupiter, Saturn, and one of them, I think it was Voyager 1, went by Neptune and Uranus. They had a cosmic ray subsystem on that spacecraft. That, by the way, is still out there, way beyond the orbit of Pluto. I mean, Pluto is like 4 billion miles away, and it's way beyond that location. But they still have been in contact, starting to peter out a little bit, but this is a count they made from Voyager 1. So here's the particle count of cosmic rays. And you don't even have to look at the absolute number, although it's per second. So here's these cosmic rays, and whoops, right about the May time period, they start increasing. So at this point, the reason for this is the heliopause, the point in the solar system where the power and the particles and the influence of the sun basically becomes no more than the interstellar medium. So this is where you're really once you get beyond the heliopause, you are outside of the influence of the solar system. Up until the heliopause, you still have more influence from solar particles than you do from the interstellar medium. So heliopause occurred right about for Voyager 1s when they were wherever they were located. I don't have the exact location, but about May of 2011, Voyager 1 said, okay, we're now going outside of the solar system. And that is called a heliosphere. So everything which is within the sphere of the sun, the influence of the sun is the heliosphere. So the same, Voyager 2, different timing because they were on different paths. So this happened in 2018. But this is the same concept. You have the number of heliospheric particles going along here, and you have the number of galactic cosmic rays, and you reach a certain point, and whoops, as the heliospheric particles drop off, because you're beyond the influence of the sun, and then the cosmic rays pick up. So they made a determination that November 5th, 2018, Voyager 2 leaves the heliosphere. I would have thought it would be over here, but I didn't make that analysis. So anyway, the whole point is solar particles drop off, cosmic rays increase. So let's talk a little bit about what happens when the cosmic rays come into the atmosphere. Cosmic rays coming down here. And we mentioned there's a lot of atoms, nitrogen especially, more so than any other atom in the upper atmosphere. So a cosmic ray hits an atom of nitrogen. And what it does, it knocks a neutron out of that atom of nitrogen, and it ends up creating carbon-14. And then carbon-14, we're all aware of, it has a half-life of 730 years. And when animals, plants digest carbon-14, and they then, trees die, they can measure the carbon-14. It is no longer collecting carbon-14, and they can measure how much of that carbon-14 has changed to other elements. So it's a way of dating plant matter back maybe 20, 30,000 years. So what happens is, here you have a nitrogen atom. A nitrogen-14 is the atomic weight, 7 protons, 7 neutrons. Neutron comes in because it was hit off another atom by a cosmic ray, and that neutron is added to this carbon atom, and it expels a proton. So this was nitrogen, but the addition of the neutron and the expulsion of one of the protons created carbon-14 from nitrogen-14. There was no carbon-14 in the beginning. It was nitrogen-14. The neutron came in, increased the number of neutrons, knocking off a proton. Nitrogen-14 became carbon-14. So that's how carbon-14 is created by cosmic rays. And that has interesting implications because the carbon-14 levels can vary then in accordance with the cosmic ray activity. If you have a lot of cosmic ray activity, then you're going to have more carbon-14 created. If you don't have much cosmic ray activity, you're going to have less carbon-14. So you can look at past carbon-14 levels, and you can indicate what that past solar activity is. If there's some way you could measure carbon-14 in past trees, and they can even measure other isotopes, not just carbon-14, other isotopes in rocks, in meteorites. We'll show you even in ice cores, in sediment samples from the bottom of the ocean. You can measure these isotopes and figure out past years, past decades, past centuries, or even thousands of years, what the solar activity level was at that time based upon the level of carbon-14. So again, low carbon-14 correlates with low cosmic ray counts, thus higher solar activity, and vice versa. High 14, high cosmic ray activity. So this is one I showed last year. The idea is low solar activity, and here's that sun that doesn't have much in terms of sunspots, flares, coronal mass ejections, a very quiescent sun. Solar activity is low, auroras are low. I say that, but you got to remember, one of the biggest solar events was the Carrington event in 1859. And that was an event where they think there was 2 coronal mass ejections. One left the sun, and then another one went off that same coronal hole on the sun, smashed into it, and made a super massive solar storm on the Earth. Fortunately, the only electronics we had were telegraph offices. So some telegraph offices either burnt down, or some of them they caused fires. Some of the telegraph lines had extra electricity, if you will, that was pulsing through those lines. If this happened today with a Carrington event, it could be quite devastating to our grid, our power systems, our grid. So you can have a Carrington event or a massive solar storm, even at a solar minimum. It more likely happens at solar maximum, but you can still have it at solar minimum. So low solar activity, low auroras, but cosmic rays are up, carbon-14 is up. And then the reverse of that is, if your solar activity is high and that side of the sun looks like, half a cycle later, with an 11-year cycle, so that's 6-7 years later, 11 years later, you're going to have a very active sun. Solar activity is up, auroras are up, but the solar activity kind of balances and prevents some of those cosmic rays from reaching the Earth. As much as a diminution, if you will, of maybe as much as 15, 20, maybe even 25% fewer cosmic rays because of that extra emphasis, energy from the sun at solar maximum. And carbon-14 is reduced. So the feds think Toyota's problems might be due to cosmic rays. That explains why you went for the tinfoil hat package. And by the way, it says this is true, not the tinfoil hat. But there was an issue a few years ago where there was an accelerator problem with Toyotas. And some people, I don't think they were maybe the Toyota company or somebody in the federal government thought, well, maybe it's cosmic rays that are causing this accelerator problem. And it was kind of funny, but however, they think there could occasionally, cosmic rays are powerful. In space, they've had activity where you have a satellite that's in orbit and it doesn't take much solar activity or even cosmic rays to shorten out some circuits and burn out some of the highly sophisticated but very electronics on satellites. It could possibly happen on Earth, not too sure, but I thought it was a cute cartoon. Okay, let's talk about the power of these solar rays, or I should say cosmic rays. So this is a map of the Earth, and what we're measuring here is we're measuring microsieverts, and I'll show you what those are in a second. But just to show you this scale, on Earth, on the surface, especially at lower elevations, you have lower doses of radiation. Right here is 0.02 microsievert, and as you get up in elevation in higher mountain areas like the Rockies, you kind of have an increase up to 0.5, 0.1 microsieverts on the surface of the Earth. And again, microsievert is, one microsievert is 1/millionth, we'll call a nanogray is, I should say, a nanogray is 1/millionth of a gray. A gray is the same as a sievert. So 1 gray is a way of measuring radiation. It's equivalent to 1 sievert. And I guess I can do both of them, but 1 nanogray then is equivalent to 1 billionth, nano is billion, 1 billionth of a gray, and a microsievert is 1 millionth, I always get backed up on that. A microsievert is 1 millionth, and a millisievert is 1,000th. And these are the way they measure the radiation. And I want to take you to the microsievert. Here's roughly on the surface of the Earth, the microsieverts are about 0.1. I've measured them before on a little dosimeter I have that shows somewhere between between 0.05 and 0.1 microsieverts per hour. That's the rate of radiation. That's if you're just measured outside the door. If you put it on granite, I heard about granite countertops that have high levels of radon. You can get numbers that are maybe 3 or 4 times higher than that because you have radon. Radon is a big issue in terms of radiation. Don't get rid of your granite countertops because of that. And this shows you'd have 0.46 microsieverts per hour. That's the rate at which it's accumulating on a bunch of radioactive beads. And this is interesting because when you're in an airplane, this is just a normal flight, and I have some other information on this, 1.4 microsieverts per hour, which is about 14 times the radiation on a per hour basis in terms of the rate of the radiation accumulation that you get on the ground level when you're up flying about 25 or 30,000 feet. And some other readings around the world. Los Angeles, 0.09, Paris, 0.1. What's really interesting, you'd expect New Hampshire's 0.3, probably because a lot of granite in New Hampshire. That's one reason why you might have 0.3 microsieverts in New Hampshire. Chernobyl, because of the meltdown there of the nuclear reactor. This one here, 30.8, is really weird. Brazil, there's a beach in Brazil where that sand is very radioactive because it's a material in the sand. So people actually go there and try to get I think, kind of a massage with the radiation. I don't quite understand that. But this is pretty high in terms of a level at the ground level. So, I don't know if anybody saw the movie Snakes on a Plane. I did not see that movie. Fortunately, Hawaii, we don't have to worry about snakes, right? Yes, question.
On the color map, why was the west coast all in pink, all the way down? It went through Mexico. It's really
Well, part of it was the mountain. You have mountains, although you have a coast area. It varies too, according to the topography, what type of rocks. So there's a variability. I mean, if I take I have a small little dosimeter, and if I'm going to take it off on an airplane, I'll have it on, and it'll bounce around. It'll bounce around between 0.5, or I say 0.05, and 0.1 microsieverts. So it bounces around. Yeah. So there's a lot of variability. Now this is a group called. Oh, there's the Geiger counter. So this is there's an organization, I'll show it to you in a second, that has taken a lot of flights around the world, and they have measured the radiation from high altitudes. So I want to go back and kind of explain this a little bit more, because we just hit quickly the million microsieverts. You got 1 sievert that's equal to 1 gray. And 1 millisievert, right here, 1 millisievert is 0.00 sievert. So that's going to be a millisievert. You know, we can deal with sieverts or grays, they're equal, but a milli is 1,000th of a sievert or of a gray. And then 1 microsievert, now the milli has an M before the SV, and a micro has that little mu. So the microsievert, microgray, is 1 millionth, from 1,000th to 1 millionth. This is 1 millionth of a sievert. Okay. Normally at sea level, you have between 0.05 and 0.1 microsieverts. And I just look at this, I made this calculation, but it's probably not, I said, okay, if an airline crew, that one airplane, that one information, but one photograph showing that the airline had 1.5 microsieverts per hour. If you figure a pilot, and this is my estimate, flies 80 hours a month, 12 months, he or she would end up having 1.4 millisieverts, okay, millisieverts. And sea level, that same number, if it's 0.114 times, that's the number of hours in a year, you would accumulate 1 millisievert over a period of a year just being on the ground. Airline crew, now some of the numbers I'm going to show you are twice this. So an airline crew could end up getting 2 to 3 times more radiation by flying frequently, especially over the poles, which you'll see in a second. One person asked me one time, so how much does it take to kill you? Okay? The lethality is quite a bit higher than this. If you got 10 to 20 sieverts or 10 to 20 grays, that could be lethal. Part of the issue is, you know, there's an accumulation of radiation, and it depends upon that. It also depends upon whether that infusion of radiation is instantaneous or whether it's over a period of time, in which case your DNA, your cells could regenerate and could heal themselves. So it depends upon a lot how much it would take to be lethal to a person. And here's again looking at it. The grays and the sieverts are considered to be used by other countries. The U.S. used rads and rems. Now, this makes it confusing because there are 100 rads in a gray, 100 rems in a sievert. So you can't really, I guess you can make the transition, but for some reason, this is used in the U.S. Grays and sieverts are used by other countries, kind of like we don't use metrics and everybody else in the world does. And what is a sievert? It's 1 joule of energy per kilogram of absorbing material, kilogram being 2.2 pounds. So that's kind of how they define the sievert. Now, this is one of the charts from that organization, Rads on a Plane, not to be confused with Snakes on a Plane. And they did some studies, and they showed that, okay, you take off from the ground, you know, you don't get much increase in radiation at 10,000 feet. I've even tried Haleakala. There's no additional radiation in Haleakala. It's the same as it is down here at sea level. But once you get up here above 20,000 feet, you do get this increase. And this is in the tropics, so this is a lower, along the equator. You have more atmosphere, and you're more protected from the magnetic field of the Earth, but you still can get up into here's the 1.2 or 1.5, which we saw on that chart with the aircraft holding that meter. But if you go to the Arctic, you're talking, upper, Alaska, Canada, upper Asia. Well, I tell you, you can go up to 33.5 in terms of the microsieverts. And see the little micro G, that's a gray. A gray is the same as a sievert, so it's the same thing. So you have 3.5, which is 35 times higher than 0.1 would be 0.1 microsievert on the surface of the Earth. So very much more radiation when pilots fly over the poles to go between the U.S. and Europe. Here's one of the U.S. compared to Sweden. Sweden's further north, so Sweden, those numbers get up about 3.5. Higher elevation too. The higher elevation you go, the higher latitude you go, the more you're going to get radiation. The U.S., same way, you can get up around 3 at higher elevation, 40,000 feet. They're kind of puzzled about Chile. Chile is relatively low compared to the U.S., and it's kind of the same latitude. Here's the equator. Here's the U.S. Chile's down here. So you would think that Chile would be kind of the same as the U.S. They think one thing may be, they don't quite know how the cause and effect, but there's something called the South Atlantic anomaly right here. It's a gravitational anomaly that satellites have to take into consideration. And that could be in something going on which causes this to be less, although I would think that maybe it would cause it to be more. Yeah, Scott, you got a question? How does this impact the people at the space station? I'm glad you asked, because I got a chart coming up exactly on that. Yep, you hit the nail on the head. So that was the question, was how does it impact the space station folks? So also, New England seems to have a higher radiation because it's it's the northeast again, you're a higher latitude. And when you're up at 40,000 feet, it's not too bad up until 30, 1.5, 15 times the ground level, but you can quickly go to 3 times the ground level when you add that extra 10,000 feet. Southwest US, a little bit less. They also say the Northwest is almost as high in radiation as New England, but they are higher latitudes, okay? So here's one that same company did, Baltimore to Las Vegas. Rapidly, once you get altitude, which doesn't take too long, minutes after takeoff, 20 minutes after takeoff, 30 minutes, you're basically at elevation or at altitude, 2.5, and it continues and it drops rapidly once you do your descent to your destination. So I put these charts together. This is what I measured on the airplane. Back in January, LAX to Kahului, I measured, I don't have a life, every half hour. Every half hour I was measuring the sieverts per hour, the rate, okay? And the cume. The cume is what gets you. This is the rate, how much you're accumulating per hour. So it went as high as 16 levels, right here, 16 times the sea level, i.e. from 0.1 in LA to 1.58, so almost 16 times. By the time the flight was over, there was 7 microsieverts. Again, 7 microsieverts, but it takes a lot of microsieverts to get enough, because we're talking, 7 millionths of a sievert. So it takes quite a bit. Although that being said, when you eat a banana, the banana has radioactive potassium 40. So you get some radiation from banana. And I did read that it takes, if you eat 80 million bananas, it'll kill you. I think you're going to die more than just be something else besides the radiation by the time you digest 88 million of those. So anyway, the other flight here from LA to Kahului, same kind of thing, 38,000 feet, 1.8 to 2.2 microsieverts per hour. As the latitude decreased, because LA is higher latitude, it actually dropped from this, about 2 microsieverts per hour rate down to about 1.5. So it drops with lower latitude. And by the way, wasn't this a great airplane I flew on? Yeah. Not really. This airplane, hopefully they plan to put this in service. American Airlines, it's called the Boom Company. And it's the Overture is the aircraft supersonic, goes 1.7 Mach. And American Airlines has put a bid in for 20 of these. It's going to be, 5,000-mile range, three hours from New York to London. I just thought it was better than seeing another Hawaiian airline airplane up there. So Iceland, again, you're going over southern British Columbia. I'm sorry for the Canadians, but 35,000 feet, 2.5 microsieverts per hour. And then before I took off, the sea level was 0.05 microsieverts. So we were at 2.5 at the rate, that's the rate per hour, and 50 times sea level. And this was flying over Torngat National Park, southern Greenland, 37,000 feet, and went up to 2.8 microsieverts. And again, it may not be enough to kill you, but it's a lot more radiation than you're getting on the ground. And I think this is the last one here, Seattle to Reykjavik. And 27 times. And how they go to Reykjavik from Seattle, they kind of go over, again, Canada. They go over near the Hudson Bay and southern Greenland. So you're getting some of that high latitude flights. That's why you're getting numbers up in the 2.7, 3, i.e. 25, 30 times the level of radiation on the ground. Okay, so let's talk about the International Space Station. Okay, these folks are definitely, they're concerned. Primarily you hear about solar storms. Oh my God, if there's a solar storm, they all go inside and they go in this leaden shield to protect themselves from some coronal mass ejection. Well, there's also the issue of rays too. The three things that affect them is the elevation, how high they are. Okay, the higher they are, the more likely they're going to be hit by powerful cosmic rays. The other thing is if we're in a solar cycle. If we're in a solar cycle, if we're at a high of a solar cycle, the risk is from the sun. If we're at the low of a solar cycle, there's increased risk not from so much the sun, but from cosmic rays. The third thing is individual susceptibility. We all have different susceptibility. Everybody in this room could be irradiated with the same amount of radiation, and we'd all have different effects. Some of it would be lethal for some of us, others it wouldn't bother at all. So there's an individual susceptibility. Okay, let's talk about safety. When I go to the dentist, every 6 months, it seems like they always want to x-ray my teeth, the bite wings. And I really don't want I figured, who needs more radiation, right? And they say, well, it's completely safe, it's completely safe. And I said, okay, do the x-rays. But then they cover me with this big lead shield, and they leave the room. I thought it was safe. So the secret of that is, next time you get on an airplane, just wear a lead suit. That'll protect you. But I will tell you another story. So when I was in the 9th grade science class, my professor teacher was Dr. Steiner. And I asked him the question, I said, okay, the old alarm clocks used to have radium painted dials. They would glow in the dark. I said, Dr. Steiner, are those safe to have on your nightstand next to the bed? He said, they are completely safe. There's no problem. But I always put mine under the bed just in case. So I don't know what lesson I took from that, but he may have been kidding. I don't know. Okay, so if you didn't see the cartoon, no fear. Space junk will help block solar flare radiation. It may help. I don't know. Okay, now let's talk about detection. A lot of you as kids, maybe even as adults, you put together a cloud chamber, Wilson cloud chamber. I had one that didn't work as well as these, but you get some dry ice and you super chill, in this case alcohol, creates a cloud, and then when you have cosmic rays come through, and then when I say cosmic rays, I'm using the term loosely because a lot of the cosmic rays, for the most part, have become muons. And muons are what the secondary particles that do hit the Earth, and just the same amount of problem, not quite as powerful as one of those highly energetic cosmic rays that hits the upper atmosphere, but they're still bombarding you. So we use that term kind of loosely. Anyway, you get this cloud of vapor, and a ray comes in, a cosmic ray, or again a proton, and it ionizes the vapor, the alcohol, and that ionization creates a little cloud, a little storm, if you will, which quickly dissipates. So that's the way they detect. I got a couple little videos. These guys are even talking about, I see an alpha particle, someone said. So these are rays coming through, or I should say they're particles again. And even more cooler than that is this one here. This has a lot going on. I think this is a radioactive source here because of the intensity of these trails of particles. So don't think those are cosmic rays as much as they are particles coming from that lump of either either uranium or maybe it's carnotite, some type of radioactive material.
I have a question.
Yes, question.
So these cosmic rays are originating millions or, I don't know, billions of light years away?
Okay, yes.
Why do they not degrade in power? Or maybe they do, over those millions and billions of light years.
Okay, good question. The question is, why do these particles from millions, if not billions of light years degrade by the time they get here? And the answer to that is the scientists are surprised at those high-powered ones. We talked about the two of them that were, 10 to the 20 electron volts. They were surprised because something that powerful they expected to come from a relatively close source. Like something, well, here's an example. This is Centaurus A, which is a galaxy that's only 13 million light years away. Really close. I mean, that's not far. 13 million light years away. It only took 13 million years for light to get here. So this is, it's got a supermassive black hole at the center, about 55 billion solar masses. They would expect the high-powered particles to come from a relatively close galactic source like that. And the fact that it doesn't, that they have the high-powerful ray that came from a void, it puzzles them because they would think if it came from that far away, if there's something in that void, even further distance, they would think that the power would have dissipated. But you got to remember, in interstellar space, there is the interstellar medium, so you're going to have some slowdown maybe. I mean, it's not a complete vacuum, but these are considered so powerful that they don't really understand. They don't even understand what astrophysical mechanism would create such a powerful particle as these particles that are 10 to the 18, 10 to the 19, 10 to the 20 electron volts. They just don't understand that because they are tens of millions of times more powerful than we can create in the large collider that the humans we have in Europe. So they're kind of puzzled, yeah.
And presumably these ones that finally make it here, or make it to the muons or wherever, they haven't collided with anything in all those millions of light years?
Well, they could have, but they think that since they're protons, they're positively charged protons, one of the reasons they can't find the origin is because they're going through a lot of different, magnetic fields, for example, and that's why they think they've taken these, I'll call it not zigzag, but these very circuitous routes to get here, and they can't really trace it back. So they are affected to some degree by fields. Now, they're affected by magnetic fields, but they feel these extremely powerful ones are so powerful that they wouldn't even be that affected by magnetic fields. Does that help explain that?
They're not colliding with anything else because that would have...
Well, the interstellar medium, there is stuff there. There's a couple of molecules every cubic meter. So there's stuff out there, but probably not enough to affect this. Just like if two galaxies collide, you got two galaxies that have 100 billion stars. If they collide, and you see what you see on photographs, you see all these tidal tails, but they think it's very rare. It happens occasionally to have when two galaxies just go through each other. It's very rare to have stars collide. What you have is a lot of the gravitational pull of these different bodies distorting gas and dust and other stars, and you see these galaxies with these long tails and with these distorted disks. But it's not because there are collisions, because interstellar, even within a galaxy, the space is so vast between stars that it would take a lot for two stars to collapse. They can almost go right through each other, and the only effect you would see would be the gravitational effect, the tidal effect of the gravity. Does that help explain that? Okay, so this is this schematic of a particle coming through, creating a lot of secondary particles. This is actually talking about the Pierre Auger Observatory, which studies these high-energy particles. And this observatory is actually in Argentina. And another schematic here where we kind of talked about particles coming in, creating a lot of muons and pions, and there's gamma rays being created and electrons being created. And one of the ways they can detect these is if you have a particle coming in, upper atmosphere, or for that matter, even a gamma ray, and we'll talk about a gamma ray telescope in a minute. have a gamma ray hitting objects in the upper atmosphere, it creates and knocks it actually the impact of that ray or particle on an atom or a molecule can release a flash of light. And that flash of light is called Cherenkov radiation. And you notice right here they have Cherenkov light. So our particles coming in, they're looking at fluorescent light in this telescope, but then they have these Cherenkov detectors, and the particle is created and the particle is a photon of light, blue light, when a particle or a gamma ray hits a molecule or atom in the upper atmosphere. This is a schematic of the field of detectors in Utah. We talked about the telescope array in western Utah. There's about 500 of these detectors. I believe they're trying to increase it to 1,000. Right now, these 500 cover about 300 square miles. They want to increase it to about 1,000 square miles in Utah to have a greater footprint on the ground so they can see more of what's going on, what's hitting the ground. And this is one of those currently 500 detectors, ping-pong-sized tables in the western Utah desert. I want to talk a little bit about gamma rays because we talked about gamma rays are rays. They're not really part of cosmic rays. But since gamma rays can, in deep space, as a result of a supernova, they can create, through the gamma rays hitting other objects, they can create particles, photons that become cosmic rays. And as you've noticed in previous charts, a proton comes in and it creates all the subatomic particles, and some gamma rays are created. Just like gamma rays are created, they didn't know this for years, severe thunderstorms create gamma rays. So, the gamma rays, are they cosmic rays? Not officially if you define it as particles, but they are rays for sure, and they're part of that mixture. And who knows where a ray creates a particle or a particle creates a ray. Some of that gets a little bit obscure. So, just to remind everybody, gamma rays very powerful out here at the end of the spectrum. So, the ultraviolet, this is 400 nanometers. That's 400 nanometers, 1 billionth of a meter. So 400 billionths of a meter. But you want to go to gamma rays? 0.01 nanometers. So this is 1/100th of 1 billionth of a meter. Or take this number here. That would be 1/10,000th of a nanometer, of a billionth of a meter. Pretty small stuff. But those are the wavelengths, and then the frequency is extremely high, and that frequency, extremely high frequency, is what can be deadly. Gamma rays are deadly radiation. Okay, I love this because it shows the whole spectrum from radio to gamma ray, different observatories we have. We're going to talk about two. Fermi is in orbit looking at gamma rays for sure, and HESS is a ground-based observatory in Namibia, in Africa of all things. It's called HESS because of Victor Hess. We talked about him, the Austrian that was from Vienna University that discovered cosmic rays. So they named it after him. The acronym then they said it was High Energy Stereoscopic System in Namibia. Okay, let's talk a little bit about, here's a black hole created by an implosion, probably a type 2 supernova that was so large that it imploded because of the gravity overtook the nuclear fusion. It created some gamma rays, and as this image portrays, these could be low energy, but then when there's a faster shell, probably what happens is the outer edge explodes, creates this slow shell, but then the implosion bounces off the center, creates an even faster shell, overtakes the slower shell, and these colliding shells then emit gamma rays. And further on, you have gamma rays, X-rays, visible light, the whole 9 yards. So somewhere in this, they think that there could be some official high-energy protons being created, although you don't really see it over here, probably down in this area here. This is the October 2022. You can watch that closely. It is a GRB, gamma ray burst. It's got a number. The number is 221009, which is the 22nd, 2022, the 10th month, the 9th day, the first one they saw. It lasted about 300 seconds. It's a bright flash, the most powerful gamma ray burst that they've seen. Usually they have low duration gamma rays, fast duration. A fast duration would be one that lasts within 2 seconds. A longer duration can go in this case up to 300 seconds. That's what, 5 minutes? So most powerful one they've measured so far. And this is what they measured up to 2 weeks later. And this is from X-rays that are left over from this explosion. And the X-rays are basically irradiating or bouncing off dust particles. And the size of this, here's 5 arc minutes. So if you take this over here, you're 30 arc minutes. The moon is half a diameter. It subtends an arc half a diameter, half a degree. And this is about about 30 arc minutes, which is the same size as the full moon. So if you looked at that in the sky, if you could see that, you can't see it unless you have a X-ray detector, but it'd be about the size of the full moon in a nighttime sky. I forgot where the source was. I don't think I have the source of that one. So Fermi, they have a large telescope, and they have decided, the Fermi telescope's been in orbit quite a while, that most of the particles they've seen are called blazars. These come from active galactic nuclei that are pointed towards us, and kind of a little bit of everything. Pulsars, collapsed stars that are neutron stars that rotate very rapidly, send out a pulsars, globular clusters, binaries, and the big thing here is 28%, almost a third, unknown origin of what they've been able to detect from the Fermi telescope in orbit. Interesting telescope. This is called VERITAS, which stands for Very Energetic Radiation Imaging Telescope Array System. This is in southern Arizona. So it's about 20, 30 miles south of Tucson, about 4,000 feet. And it's got 4 of these mirrors. They're basically mirrors that are 10 meters in diameter. So that's about 40 feet in diameter, just a little bit less than that. And these are called, they're really Cherenkov telescopes, because what they're doing is they're looking for flashes of blue in the upper atmosphere, because that would be the Cherenkov radiation that's created when a particle, a gamma ray, or maybe even a photon, hits the upper atmosphere and creates that flash of blue light. This is Cherenkov radiation. If you've ever had the privilege to go to a nuclear facility where they have tanks of water, 10, 20, 30 feet deep, if not more, and they have these large tanks where they're holding radioactive material, and these tanks are made of iron and concrete, you still get radiation coming through those, and they're creating this Cherenkov radiation. Well, the water glows, it glows blue. Because you have that the radiation, it's almost what's happening is within the water, the speed of light is less than the speed of light in the atmosphere. But these Cherenkov, this radiation, these photons of light, actually go faster than the light goes in the water. They don't go faster than the speed of light in the atmosphere, but they go faster than the slower speed of light in this water, creating this blue glow. Quite unusual. I had the privilege many years ago, Oak Ridge, Tennessee, to do a tour, and I was shocked looking down this big vat of water, and the water is glowing blue. Oh my gosh. That's the Cherenkov radiation. Okay, this is a little video too that tells about some of the things they're doing in space to measure.
Hold out your hand for 10 seconds. A dozen electrons and muons just zipped unfelt through your palm. The ghostly particles are what scientists call secondary cosmic rays, subatomic debris from collisions between molecules high in Earth's atmosphere and high-energy cosmic rays from outer space. This daily shower, which never stops, is a sign of violent events in deep space. It's believed the majority of cosmic rays come from supernova explosions. When massive stars explode, they blast most of their material into space. The expanding shock waves can break apart interstellar atoms and accelerate the debris to unimaginably high energies. Other unknown cataclysmic phenomena may be at work too, especially for the most energetic cosmic rays. Eun-Suk Seo, a professor of physics at the University of Maryland, says, cosmic ray particles with energies as high as 10 to the 20th power electron volts have been measured on the ground. This is more energy than we have achieved in the most powerful man-made particle accelerators. But how do natural cosmic ray accelerators pump so much energy into these particles? This is one of the biggest mysteries in astrophysics. While indications of the energies of cosmic rays can be measured from the ground, Seo and colleagues have taken their study to higher elevations. directly measuring particles from space before they break up in Earth's atmosphere. The cosmic ray detector known as CREAM, the Cosmic Ray Energetics and Mass Investigation, has been launched to the stratosphere above Antarctica on board long-duration helium-filled balloons. By lofting the detector above 99% of the Earth's atmosphere, researchers get a better idea of what cosmic rays are like before they collide with nuclei in the air above the detector. CREAM is able to measure the energy and direction of each incoming cosmic ray particle and identify the particle type by measuring its charge, thereby providing clues to the particle's origin and acceleration mechanisms. Since 2004, the team has flown CREAM 7 times over Antarctica, accumulating more than 191 days of data from altitudes as high as 120,000 feet. They're about to go even higher. CREAM is heading for space. A reconfigured CREAM detector is scheduled to travel to the International Space Station in 2017 aboard SpaceX's Dragon spacecraft on a Falcon 9 rocket. Named ISS CREAM, it will remain installed on the Japanese experiment module, also known as Kibo, for at least 3 years. SAW says the ISS provides an excellent monitoring platform for high-energy cosmic rays. The station allows for long-term monitoring in lieu of multiple limited-duration balloon flights, providing direct, unimpeded access to incoming cosmic rays without atmospheric interference. The longer exposure times on the space station allow for the measurement of higher energies. ISS CREAM has a goal of measuring the highest energy possible for direct measurement of high-energy cosmic rays. She adds, the mysterious nature of cosmic rays serves as a reminder of just how little we know about our universe.
So, if you Google ice cream, you're going to talk with astronauts, you're going to get something about astronauts eating ice cream. So, you have to, it's ISS CREAM, kind of cute, they call it ice cream. And by the way, this was a satellite that's still in orbit, Advanced Composite Explorer, and they think it's supposed to have a life through the end of 24. I think it's still up there, but it's probably close to the end of its life, looking at cosmic rays in various forms of interstellar radiation. This one here just went 10 years. The ice cream is interesting. It's supposed to go 3 years, but it only went about 18 months because there were some not technical problems. There were some political issues. Because between the principal investigator and whether it was the Japanese it was on their Japanese unit in the space station. Anyway, it was canceled after 18 months, which is too bad. There was a 2011 launch of the Alpha Magnetic Spectrometer, which is still on the space station and taking measurements of cosmic rays. And so they're trying to also look at antimatter that's in space coming towards the Earth. So these are some of the things that are ongoing or that have been ongoing. This is also fascinating. They've actually looked at the number of rays versus atmospheric pressure. And you can see the count here, the counting counts per second. But there is a decrease given higher atmospheric pressure. So higher atmospheric pressure seems to decrease the amount of rays that they can measure. And cosmic rays in terms of cloud cover. So if you have a 5 or 15% change in cosmic rays, it looks like it can result in a 2% change in in cloud formation. I thought that was fascinating. They think, as I mentioned before, we didn't know until relatively recently that gamma rays can be created by particles in clouds. And they're thinking that cosmic rays may have something to do with this. And I've got a kind of a short video which talks about cosmic rays and lightning. This isn't very long.
Ben Franklin began the study of lightning 260 years ago, but to this day, scientists still don't fully understand how it forms. Sure, the basics are known. It's like a zap of static electricity, except on a much, much larger scale. In stormy updrafts, raindrops and ice particles rub together. Some become positive and others become negative. Then they're pushed apart by wind within the storm cloud. As a result, the cloud ends up with areas of different charge. Lightning is the spark that jumps between these areas. These sparks can also fly between the negative areas of the storm cloud and the positive areas on the ground, say through a tree or a golf club. Simple, right? But there's a problem. The electric fields measured in thunderstorm clouds typically aren't big enough to trigger a spark. So what sets it off? Maybe cosmic rays. The idea goes like this. Cosmic rays, which constantly bombard the Earth, produce fast-moving, highly energetic electrons. These electrons collide with air molecules, which produce more speeding electrons, and so on. This process is called runaway breakdown and leads to an avalanche of energetic electrons through the air. These electrons forge a conductive path in the air, which triggers the discharge of lightning. Of course, the theory hasn't been proved, and there are other ideas for sparking mechanisms as well. It will take more work to fully solve the puzzle of how lightning forms. In any case, remember, the next time you get zapped pulling on a wool sweater, it just means you momentarily caught a little bolt of lightning. For Scientific American's Instant Egghead, I'm Philip Yam.
Takeaway there is fascinating that they don't quite think that there's enough electrical discharge differential in a cloud to create lightning. They think maybe it's being primed, if you will, by cosmic rays, cosmic particles. So, historically, they can go back and they can look at tree rings. We kind of alluded to this before. And they can look at ice cores, and they can look back in terms of trees, probably a few, like 10,000 years, maybe not quite that far. Ice cores, I think they've gone back a few 100,000 years, and they can look for these cosmogenic isotopes. And if there's an increase in isotopes, they can say, in this time period, there was an increase in cosmic rays which caused these isotopes to increase. Or there's a lessening of those isotopes, in which case fewer cosmic rays, and they can relate that to the solar cycle, since there's an inverse relationship between the cosmic ray frequency or number and the solar cycle. In addition to ice cores and tree rings, they can do sampling in deep sea sediments and get the same information. And meteorites. They can look at meteorites and they can do the same analysis. And the thing about meteorites, they can actually measure what's been happening as this meteorite was floating around in space in terms of having isotopes being created. So there's different ways that they're investigating to find out what the nature historically back thousands of years, maybe hundreds of thousands of years. And just the sources, this is that supernova 187. It could have been a source, and this, by the way, came from the Large Magellanic Cloud, and this is the Tarantula Nebula in 1987. I don't mention that anymore, but this is a potential source, supernova such as this one here. The closest supernova in the last few hundred years, and it's been the most highly studied supernova because it happened so recently. And they also, over time, the solar system and the sun take about 200 million years to orbit the galaxy. And as we go around the galaxy, we are going in this path that varies. It goes away from the plane of the galaxy, and it goes back, dives back below the plane. So it's getting different amount of rays, radiation, depending upon what it's near as it goes through its path. They think that this oscillation, if you will, is about a 60 million year period. So by the time the Earth goes around the galaxy once, this oscillation has occurred like 3 times. So again, this is going to create some differential rays over time, not over our lifetime, but over millions of years. And as our galaxy, the Milky Way galaxy, moves, we're moving towards this Virgo cluster, 54 million light years away. We're going to be increasingly bumping into more and more galaxies. We can expect to have more and more cosmic rays and radiation. And real quick, this is fascinating, muon tomography. Because these muons are so common, they can put detectors, for example, this pyramid, they can put detectors around this pyramid, and they can detect, and they did in this case at this pyramid in Egypt, a large void, a large cavity where there was perhaps some pharaoh buried within this pyramid. At similar light, Mount Osama in Japan, they have, using this tomography with muons, they have taken a look at the details of a volcano. For example, right here, only about a month apart, the analysis with this tomography shows that there's an increased amount of magma forming in the bottom of that volcano, right here in the blue, because it's less dense. Magma is less dense than solid rock than it was a month earlier, projecting possibly an eruption because of that. So this tomography with the whole idea about these muons has many, many applications. They can even use these to examine large containers to see if they have any contraband materials. Large containers at shipping ports. Okay, so real quick, a couple charts left. If you're interested more about cosmic rays, a couple pretty good books. Invisible Visitors from Outer Space, 2021. Amazon rating, pretty good, 5 out of 5 from 4 reviews. And this is a good book too. I've actually read both these. Amazon rating, 5.5 out of 5. No reviews. I've assumed a 5.0, okay? So a couple books you can look at, available Kindle, paperback, online. Now, if you take a shower tonight, you're not only taking a shower in water, but chances are you're going to be taking a cosmic ray shower. So you're singing in the rain, but you're also singing in the cosmic rays. So anyway, any questions? That's the, yes, question.
So, Mr. Musk is talking about wanting a spaceship going to Mars with people on it in the near future, according to him. What are the problems with cosmic rays on that journey?
Okay, so the question is, Elon Musk is talking about going to Mars, and it's soon, relatively soon, I guess. He's actually I've read some quote one time, he wants to die on Mars. I won't say anything else about that, but it's going to be problematic. I mean, a lot of scientists are saying it's great to want to go to Mars, but it's one thing to be in orbit around the Earth. You can get back quickly, I guess, or if you're on the moon, and once you get onto Mars, you can dig probably a lot of the habitats are going to be underground, because Mars has a very light atmosphere, but you're gonna have cosmic ray issues. You're gonna have solar issues. So you're gonna have to protect the astronauts and the people. Living underground might be fine. You can occasionally pop up with a spacesuit and walk around Mars, or have a vehicle to explore Mars that has some protection, a big old cage. But it's going to be a problem getting there. You're going to have a lot of shielding around that particular ship that's going to take a couple of years to get to Mars. Yeah, I mean, and I think some of the ships, the space station, I think has a special room that if there's a solar storm, they can send the astronauts into the solar storm for a few hours. But I don't think we could have that where it's going to have to be a longer term period between us when we go to Mars. This is going to take a couple years to get there. So it's going to be a problem. I think humans will eventually solve it, but it's considered to be an issue. Yeah. Okay. Yes, another question.
The void that you talked about earlier in your talk, where cosmic rays were coming from a void, could that be a void of dark matter that we just can't see?
Okay, question is, the void we talked about where they think some of these high-powered cosmic rays are coming from, could that be dark matter? Chances, that's a good question. I would say probably not, only because a lot of the dark matter forms with galaxies, like a halo around galaxies. That's not to say that there couldn't be some dark matter all by itself in that void. But I don't think they believe that's a void is because of dark matter. I think that's an absence of galaxies. Yeah. Yes, question.
So you mentioned that black holes can be a source of cosmic rays. Having grown up with far too much science fiction, I'm used to thinking of a black hole just sucking everything in. So how would a cosmic ray get out?
Okay, so the idea is you have a question is how would a cosmic ray get out of a black hole or radiation? So the black hole, you're right, it's a gravitational well. But the only reason we know that black hole is there, because it's black, right, is as things are being sucked in, it creates a lot of radiation because you're heating up a lot of material, whether it's other planets or even it's gas, it's dust. It's being heated up at high temperatures. That it's emitting that material as it goes in, before it goes in, it's emitting X-rays, it's emitting radio waves, probably gamma rays. So it emits stuff as it's being, I'll use the word heated up, as it's being agitated, being pulled in. Once it goes beyond the event horizon, it's gone, and you don't have anything coming. So it doesn't, any rays, cosmic rays or radiation coming out of the black hole, it's not out of the black hole, it's out of that ring of material that's being sucked in. Yeah. Okay, look, yes.
Just a comment. I listened to an episode of Radio Lab, and they're talking about how cosmic rays flip bits in
Yeah, absolutely. The comment was, there was a comment, it was on YouTube or?
It was on a Radio Lab podcast.
Okay, the podcast, that as the chips get smaller, which they're getting really small, then they're more susceptible to cosmic rays because you have a smaller. It's a good question. So well, that's it. I mean, it makes sense, but I'm not too sure if I can explain exactly what's happening. The smallness makes it more susceptible because you have smaller distances involved, perhaps, and it doesn't take as much power, perhaps, for that muon or whatever to disrupt the system. I don't think tube technology. Remember the old tube? You don't remember tube technology. Take the tubes out of the TV set. I don't think the tube TVs had those issues when you had vacuum tubes. Maybe not even traditional transistors. But as we get smaller and smaller, yeah, I've read that too, that they think there could be an increasing problem as the microelectronics gets more miniature. Yeah, that's a good point. Thank you. Yes, Larry.
Going back to the trip to Mars,
Okay.
NASA, I believe, has a lifetime rate dosage of
Okay.
radiation, like 600 millisurface, right?
Okay.
And with our current shielding, we know that we will probably way surpass that. 6 months there, 6 months back.
Right.
A lot of what I have read suggests that the best time to go to Mars would be during like a solar maximum for two reasons. One, as you mentioned, we're not putting off as many cosmic rays from the sun during the solar maximum, but also during the solar maximum, you have a little bit more solar pressure in your heliosphere. So they believe that those outward particles will collide with some of the incoming cosmic rays to de-energize them to help prevent that secondary radiation. Have you investigated?
Well, it kind of reminds me of the chart that I showed before, that as you get beyond the heliopause, you know that part where the pressure of the sun basically
It's less as we go out.
it drops off and the cosmic rays increase. So, but before you get to that point, yeah, the cosmic rays, once within the heliosphere, the sun is actually keeping 25% of those cosmic rays, if you will, from the one chart. They're keeping it at bay. And I guess your point's good. It's probably better. The solar radiation is going to be less intense, less lethal than some of the cosmic ray particles. So if you go during a maximum, you're going to get the maximum benefit of the sun helping you keep those cosmic rays at bay, at least about 25% up. Yeah, that's a good point. Yeah. Any other questions? Going once, going twice? Okay, well, yes, question.
Any other benefits of cosmic rays? You talk about radiation, but also carbon-14 are very popular things that come out of it.
Oh, I think there's a benefit because you got carbon-14 dating, and you can also look at these cosmogenic nuclides, which are the isotopes being created. I think the muon tomography is fascinating. They're using those to investigate, I didn't even show it, but to investigate these storage containers, these shipping containers, what contraband might be in there, to study volcanoes, find out what's going on in the volcano. Is the magma increasing? Is it ready to blow? And also investigating archaeological sites. So I think there is a benefit. There's always a benefit, even though we're living with cosmic rays, and they're not good or bad. They just are. Like I've heard right recently, an interesting quote: "The universe isn't good or bad; it's indifferent." Right? So the universe is indifferent to us. So yeah, there's always positives, all negatives. Yeah, good point. Yeah. Any more questions? Okay, it's been a long day. Thank you all for hanging in there. We'll see you later.